Welcome back to Physics 142 Online. Having talked a little bit about the physics of capacitors, the way they store charge, the way they store energy, how the charge is related to the potential difference, we're now going to look at combinations of capacitors in circuits. And the typical circuit will be some arrangement of capacitors connected up to a battery or power supply, which then charges them up to certain final charge values. And if we know what the final charges on the capacitors are, we can calculate how much energy is stored. So first, let's consider the two possible ways capacitors can be connected. The first is in series, where the terminal of one capacitor, the conductor of one, is connected to the other one, and the two outside conducting surfaces then go out to the rest of the circuit, and perhaps, in the simplest case, directly to a battery. In parallel, each of the two sides of the capacitor plates are connected to each other, and then to the rest of the circuit. And so you can see why one is called series, because they're back to back, one after the other, in serial fashion, the other in parallel because of the sketch. The connectivity implies that we have them oriented parallel to each other. And the way that these capacitors behave when connected to a power supply is quite different. And so we'll study that very briefly in this presentation. For example, if we look at a circuit where that series combination of capacitors is connected directly to a battery, we can see what this looks like. And the sketch does not show a switch, but you can imagine that initially the switch was open, so no current could flow, and then we close the switch and charge flows. Of course, we would see negative charge flow from the left-hand capacitor on top, the upper left, towards the positive terminal, the battery, and then through the battery, and then negative charge would flow away from the negative terminal and be deposited on the right-hand plate of the right capacitor. In response, then, there would be charge flow in the inner terminals, the inner plates of the capacitor as well. And we'll talk about what the equilibrium situation looks like in just a minute. So, here is exactly that series circuit. Now, what we can do when we have capacitors in series or in parallel is construct what's called an equivalent circuit. And what this allows us to do, if we have a power supply and then two capacitors here connected in series, we can replace the two capacitors in a sketch with a single capacitor that has the same effect on the circuit as the combination of the two original capacitors have. And so we don't physically disturb the circuit and put in a new capacitor. All we do is we mentally perform this replacement so that we can analyze the properties more easily. And the big question then is, how is this equivalent capacitance related to the two original capacitances? So there's a very simple relationship that we can form if we know that the potential difference generated by the battery across the terminals of the battery is delta V. Then we also know, through a very simple consideration, that the sum of the potential differences across the two capacitors has to equal the potential difference across the battery. And they have to be opposite in sign. So in other words, if I go around this circuit in the clockwise direction, as I cross the battery, I'm going up in potential. So there's an increase in potential, delta V. Then, as I go from the across the upper left-hand capacitor, I'm going down in potential, an amount delta V1, and then I'm going down in potential again, an amount delta V2, as I go across the second capacitor. And then that brings me back to where I started. And so the potential at the negative terminal of the battery is the same, and so the circuit, as I go all the way around that circuit, I have to end up at the same potential I started with, which means the overall change in potential has to be zero. And that's what this equation is specifying. So negative delta V is equal, or actually what I should say is that delta V1 plus delta V2, the sum of those two potential changes, is equal to the potential change across the battery. And so we can set it up, though, that making one complete loop around the circuit gives us a sum of potential differences equal to zero. And you may have seen this in a class before. We'll recognize this when we talk about DC circuits as Kirchhoff's voltage law. So anyway, it's also an expression of energy conservation, because as a consequence of this, if you have a charge that goes all the way around the circuit and comes back to where it starts, its energy stays the same. So its energy goes up as it goes across the battery and then goes down as it goes across the capacitors, and so the energy is conserved in the process of going around a circuit loop. So what we can do with that, of course, is write that delta V is equal to delta V1 plus delta V2. So if the battery supplies 9 volts, maybe one capacitor will have a voltage of 6 volts and the other will be 3 volts, and they'll add up to the original 9 volts. It depends on the capacitance values. Now, using the definition of capacitance, C equals Q over delta V, we can solve for delta V and write it as Q over C. So Q over C, where Q is the total charge that comes out of the power supply, and C is this equivalent capacitance value for the capacitor that's replaced the two original ones. Q over C is equal to Q over C1 plus Q over C2. And how do we know that this Q on each of the two capacitors is the same as it would be on this equivalent capacitance? We know that because in both cases, the amount of charge that leaves the power supply has to be the same. The equivalent circuit has to have the same effect as the original circuit. And so the charge Q that left the battery here has to also leave the battery in this case. And the reason that those two charges on the two capacitors are the same is in equilibrium, the charge will flow until a balance is reached. And if we look at the two inner plates of these two capacitors, we can see that they are both connected with an ideal wire, and so they have to be at the same potential, and that then, in order for equilibrium to be reached, would mean that those two charges would be equal and opposite to each other. So, because that overall strip with the two plates and the connecting wire has to be neutral, so whatever negative charge there is on one side, there's also a positive charge on the other side that's equal. So what does this mean here? If that Q is the same in all three of those terms, then we can cancel it out because those capacitors all have the same charge. So we end up with this curious reciprocal relationship that says we can calculate the equivalent capacitance by making 1 over C equal to 1 over C1 plus 1 over C2. All right, so that is the way that capacitances combine in a series circuit. In parallel, right, we can do the same sort of thing. Imagine that we have two capacitors in parallel that then are connected in this fashion to a battery. Because these wires connect the terminal of each of the two capacitors to the battery, all three of those points have to be at the same potential. And then the same thing is true on the right-hand side. And so whatever the potential difference is across the battery, the voltage across the battery, that has to be the same as the voltage across each of the two capacitors. And in fact, circuit elements that are in parallel will always have the same voltage across them. So if we replace these two parallel capacitors by a single equivalent capacitor, once again we would like to calculate how C is related to C1 and C2. Now in this case, because they're connected in parallel, the potential difference is the same across them, and that implies if they have different capacitances that their charges will be different. However, the sum of the two charges will be the same as the Q over here in the equivalent circuit, and we'll use that as our starting point. The reason I know this is because charge is conserved. Whatever charge there is that leaves the battery in the net sense, we'll call that Q in the equivalent circuit, is the same as the sum of the two charges that leave the battery in the original circuit. So charge is conserved. And then we can use, from the definition of capacitance, we can solve for Q and get Q is equal to C delta V and replace each of these Q terms. So we have on the left-hand side C delta V, where delta V is the voltage or potential difference across the battery. That's equal to C1 times the potential difference across capacitor 1. We already argued that that's the same as delta V across the battery, plus C2 delta V, and notice the delta V terms are the same. Capacitors in parallel have the same voltage. So we can cancel that delta V out, and we get that the equivalent capacitance for two capacitors that are arranged in parallel is equal to their sum, C1 plus C2. These formulas for series and parallel arrangements of capacitors help us to simplify complicated circuits by redrawing them in a way that replaces two or perhaps more capacitors by a single equivalent capacitor. And we often need to know not just these capacitance formulas, but the formulas that they're based on. For example, the idea here that the total charge on the equivalent capacitor is the sum of the charges on the two original capacitors. That's important, and that helps us solve certain kinds of problems. So, here's an example problem similar to what you might find on the next homework assignment, and it's going to be a little bit complicated one because we have a power supply that supplies 20 volts connected to what looks to be two capacitors in series, but then that equivalent capacitor in parallel with a third capacitor. And then if we replace that parallel arrangement with an equivalent capacitor, that would leave us with three capacitors in series with the power supply. And so often there are multiple steps involved in solving a problem like this because the first question almost always in these problems is, given a certain potential difference, when equilibrium is reached, find the final charge on each capacitor. Because if we find the final charge, it's easy to find the potential difference and then also easy to find the energy stored. So I'll be posting a video with a simple example problem, a little less complicated than this, to give you help getting started on these problems. I'll see you in class.